minus xj times gamma j.
Could you explain the first step again? I mean, what is, how are you getting that column?
So I'm going to check every column. For every column of x, so I have my input, I have y and I have x. So I'm going to check every column of x, and I'm going to take its dot product with y. And I'm going to find the one that maximizes this. So this is the column that tells me has the most correlation with y. So it's probably the most explanatory of y. That means it's most likely to have a 1 here, or some information here that's non-zero. If it was 0 here, it's unlikely to have correlation with y. Okay? And so then I've understood this correlation from this column with y, so I want to factor this out. So now I have this residual here, r. And then I want to repeat. Okay, so actually what I'm going to do is the first 0 step, I'm going to set r equals to y. And then instead of y here, I'm going to use r in each of these situations. So then I can repeat here, and every time I'm going to have some explanation of what I have, and then I'm going to factor out this explanation. So this is kind of this, it's a very greedy algorithm. I'm picking the one that has the most explanation, I'm factoring that out, and then of all the information left in y, which is now captured in r, I again find the most explanatory column. I find the best label for explanation, and maybe in some cases I always set this to be a 1. And then I factor out that explanation and I repeat. Okay? And so there are some arguments that if you, because there's some randomness arguments and they're kind of complicated, there's why they actually work, but if you set the value of n large enough, so this dimension I can make as large as I want, the more I do this, the larger, the harder it is for a 0 to be correlated with y. I'm going to be able to recover these ones. I'm going to be able to recover these ones exactly. And so it's pretty surprising to see it work. So I can actually recover all the ones exactly if my value n is large enough. And so this, what I've outlined here, this algorithm, where I've taken some, I'm trying to solve for s here. Right, so basically my goal here is to solve for s to minimize, say, some explanation y, x, s transpose. Right, so this looks like a least squares problem. Right, if I wanted to solve this problem, I could just run, on the typical least squares way of doing this. But the problem is that there are more variables here I'm trying to solve for than there are these linear equations. So I should be able to do it.
So if you're using x for solving this, x is more large than s. Why are you using x?
So x is something like it's think of this as knowing what your hardware in your camera is, right? So when you're taking a picture, all you get are the pixel values, but you know where these pixels came from because the camera has a lens, it has all these sensors which are aligned in this rectangular region. That's kind of telling you something about your hardware, how you measured it.
So instead you could have just kept s, right?
Well, so sometimes the taking of the measurement is harder than is otherwise. So, so you want to take fewer of these measurements before the kids move, because it takes a certain amount of time to make an exposure of this measurement. So you want to minimize the number of times you actually capture the information. And that corresponds with the number of rows. You could have done each pixel individually, but you're kind of taking them as a group.
So I'm guessing taking measurement is expensive, not.
Yeah, so you're in the regime where taking the measurement is expensive. And maybe you can pre-share X. You can use X over and over again, right? So you can think of, it's random, so, you know, in theory you should generate fresh every time, but really you can generate the random X once and use it over and over again, like it's part of your hardware. So then all you're getting out is you know something about your hardware, which is X, and you're getting out this short vector Y to recover this long vector S. Right, so maybe this picture is actually like, no, so this is much shorter than this. Okay, so you're trying to solve this, and this algorithm here is called orthogonal matching pursuit. Okay, so you're kind of greedily trying to solve for these values of S. Okay, and you can stop. So you keep doing this, and you should be able to stop if this residual hits 0. So the reason it might work is because you may only, get these. You're only going to get the values in a few spots, and then the others you assume 0. Okay. So also, if you have a noisy signal here, and you want to do something like these squares, but your goal is not necessarily to tell you which of the pixels or which of the values are the most important towards what you've measured, then this kind of gives you these most explanatory of the variables. This is a greedy way of doing it. So you're finding the most explanatory variables in your data set S. So in the data you have, by doing this random measurement and then trying to, or even if you have this non-random measurement, you're trying to, this is the thing you want to minimize the error at the end. You want to, so like least squares, you want to minimize along this y-coordinate, and you want to find which of the parts of X are the most important, right? So you can say, you're not trying to recover S, you have this data, and you're trying to predict this value Y. So in the least square solution, we're trying to find these coefficients of each of the columns of X. So it's a similar problem, except in the least squares, typically it's tall and skinny, and then you're not going to be able to recover it exactly because it's over constrained. So you want the solution that has the least squared error. Now it's under constrained, but you can solve it because it's sparse. But even if it is over constrained, you can still run this, and you'll only put coefficients for the columns which explain the data the most. Okay? And there you may solve for this instead of putting this 1 in this place here. You could also do other things, and if you do something like so if you do something like Tikhonov regularization or the ridge regression like we talked about, you put this regularization term, so you don't want gamma to be too big. You still want to minimize this. So doing this will actually work better, and actually putting this as a 1 norm, then this is what's called the lasso technique. We'll talk about this on Monday in the context of kind of a more robust form of linear regression. It will also tend to minimize the number of coefficients you have if you do it directly, but you can also solve it in this way, which is iteratively. We'll kind of build on this idea next week, Monday, and look at this for these over-constrained linear regression columns, where this compressed sensing works on these sparse, under-constrained columns. Okay, so this is probably a little bit mystical here. So, and this is a good chance for me to kind of go through and do, to show you some stuff in MATLAB, how you'd actually do this with matrices. Like, you know, you're seeing these things like multiplying matrices together, taking dot products and coding that in Java may be a pain, even if you are using one of these they probably have some matrix libraries in there you could use, but. Try this one too. See which one. Oh. All right. Okay. All right. So this is. So is it better if I change the light somehow? You'll be able to see it better? Does anyone know? Is that better? Okay, cool. All right, so if I want to write a matrix, let's do that. So if I have a signal S, it looks like this, right? So it's you can do a lot of stuff on command line. You can also write small files as functions, right? And if I want to do S transpose, I do this, and then it writes it as a row. And you see this is 32 elements, and there are only going to be, I think, 8 ones in here. Okay, and then I pre-generated measurement matrix X, which looks like this. And so then X times S transpose X times S transpose X times S, yeah, looks like this. So this is my value Y, right? So I can store this as Y. And so now I'm given, so now I'm going to ignore the value S and try and reconstruct it by just looking at Y and X. Okay, and so if you want to, so how did I generate X? So I wrote a small function that did this, and let's see if I can find it. So I wrote a small function like this. You call the file the same typically as the function. It's going to output Y and X. It takes an S, a D, which is the dimension of my signal, and N, the number of measurements I want to take. And so I create a random integer matrix between -1 and 1. That's N by D in dimension, and then Y is equal to XS, X times S. Right, so if I write YX equals measure S 3220, then I'm going to get all these out. Right? So it shows you Y, shows me X here. And then so this was a new one that was randomly generated. And then to try and recover this, I wrote a program which arguments. Which this takes in Y, X, some number of iterations that I'm going to run this algorithm, and then this dimension, right? And it's going to output this estimate T, right? So I'm going to set T equal to this. So. Okay, so let's see how well I did. Probably not that well. So here's where I have errors. There are 8 ones. This one I missed one here, I missed one. So I have 5 errors. So I recovered 3 of them, and I have 2 false positives. So on a small scale, actually this orthogonal match pursuit is not the best algorithm, and I really need some factor 20, so I need a really large scale before this works. If you use the lasso, where you have something like this L1 regularizer in here, which is a bit harder to solve for, then you need a lot fewer measurements, and you're more likely to actually get the recovery. Okay, so please stop if you have any questions about how this MATLAB or stuff works.
So the number of iterations, is it n?
So I set the number of iterations to d, my guess of d. You can set it a little bit bigger. You can actually say, so if it actually works, if your n is big enough that you believe it should work, you should be able to say when the residual is 0, you should stop. But if if n is not big enough, you're actually going to get some errors. You're going to falsely identify some of these things. So this find a column may actually give you something that has a 0, and that's what happened here. I subtracted t from s, and so in the third column of x, I predicted there was 1. So this ends up in t, my estimate, and I've subtracted it, so I have a -1 here. So I falsely predicted a 1 here when there shouldn't have been. And that's because I didn't have enough columns. So if I go back and I run my measurement again, say with 200, if you put a semicolon, it doesn't print out this one. Okay, right. So then, and now I ran orthogonal magic pursuit again. And so I ran it 8 times. Let's see if this works now. And so now s prime minus t prime.
That is m times.
Right. So oh yeah, m. Yeah. I'm sorry, I mixed up m and d. Yeah. So you roughly run it m times. But the thing is, you don't always know what m is ahead of time. You may guess it's some small number. So you rarely want to stop when the residual gets 0. So I ran it with 200, and I should be able to recover it exactly, right? It's now an over-constrained problem. So that maybe is not so surprising. Okay, but I pre-generated one example where this measurement matrix x1, which is only 20 rows, okay? So this is x1. I set y1 equals to x1 times s. Okay, and now I run this with x1, and I tried a few of these until I found that worked. And this one should have s prime minus t prime. It's going to be all zeros. So, you know, if you can still get lucky with the small scale, in practice you need something large. Okay, so let's see how to actually do this. So kind of step by step here. So the first thing I want to do is create a variable r instead of y that I'm going to be playing with. And actually, let's use y1 here. Okay, so I have this r. And so then I want to, so I'm going to try and find this first step, find the column which maximizes this dot product. And I actually want to maximize the absolute value of this, the absolute value of the dot product. If it's very negative, that could be interesting too. So that might mean if I have a -1, I guess. But so I didn't know actually how to run this command, and I had to kind of look this up. And if you're not sure how to do something, you go into like, you type, kind of find maximum of a row in MATLAB in Google, and there's a Stack Exchange question where someone answered this, and it's really weird notation, and you get out. Turns out this doesn't work. I want to use X1. Okay. So it found that the column, so the sixth column, which corresponded, the sixth column of X1 seemed to have the most correlation, is what this J value was here. Okay. So one kind of important thing about MATLAB, and the only tricky thing about it, is that you can write for loops in it, but it's very slow to use the for loops because it kind of is reading through your file and reads through each time through the for loop. It's not compiling it into a binary like you would in C. And when it compiles it, actually unrolls those for loops, so you don't have to keep checking every time. So for big for loops, you actually, for anything with a big matrix or a vector, you want to call a specialized function that will find the maximum value out of it. And so this max kind of is pre-compiled to do it efficiently without having a for loop that you actually have to write. I could have written this by writing a for loop and checking every element and find the maximum, but it would be more efficient generally to use some built-in command to do it. So you should always try and do that instead of manually going through for loop. Okay, so I found this, and I'm going to guess that the coefficient in the sixth spot in S is going to be 1. So what I'm going to do is I'm going to set this, start with this T matrix, which is going to be my guess, which is going to be 32 by 1 is all. So this is, I'm going to create this T matrix, this T vector, which is 32 zeros, and then T of J, I'm going to set to 1. Okay, so I set the sixth element to 1 because that has the largest correspondence. So instead of actually doing a least squares solution here, which I could have done, I kind of know that my signal is 0, 1, so I'm just going to set this to be a 1. Okay, and then I want to update my R, so I'm going to do R get R minus X. Okay, so when I do this notation, X1 is now this X1 is this matrix, and I want to kind of access the jth column. So I put a semicolon to say I'm going to take all of the rows and I'm going to take the jth column. And you can instead take a row by putting the ith row by putting I here and a semicolon in the second step. And so now this is subtracting off my guess of the effect of this sixth row here. And gamma j was 1, so I could have multiplied this by 1. It's not going to make a difference. Okay, so now this is my new R, my new residual, and then I can repeat this approach. So then I go back to this step. So if you just hit the up arrow key, it'll go back to your previous command, which is like a command line. And I'll repeat this, and now the 21st column is doing this. So I go and I set T 21st row equal to 1. Okay, so I set 1 equal to 21st one, and then I'm going to repeat this again. And I updated my R. Okay, and then let's try this again. So now it's at the 23rd one. Factor this out. My R, those values should keep getting smaller and smaller every time I do this. So now it's at the 20th. 30th here. So ours keeps getting smaller and smaller. So ours, I've almost fully explained R now, right? So R is all zeros already. So I've already completely explained it. So now if I look at T, so this is after I guess I did 8 steps, and now S prime minus T prime is all zeros. So I've completely found S by just looking at this random measurement matrix X and this column Y. So it's an under-constrained system because I had only 20 rows of X, but I had 32 things in Y in S I was trying to figure out. Okay, so then instead of doing this, manually, you can write this function that looks like this. Okay, so you set T to be all zeros, set R, and then this is a comment. So this is the first step. So then you can write these for loops just like this, and you go through this T times, which T is the number of iterations I do. And so I did something different where I took I probably didn't need to do this, I don't know. I did this late last night. I probably don't need this absolute value. Okay, so if instead I wanted to do some, so I could instead, all I needed to do if I wanted to replace, so I always assign gamma equal to 1, but I could have instead, if my input was not necessarily 0, 1, I could have solved for the value of gamma here. And remember, if you remember from the linear regression part, this is a linear regression solving for gamma, and it turns out this expression is what you do to solve gamma. Now this is going to be a little bit noisier. It's probably going to give you some value that's not 1. And so one option you can do is, so sometimes what will happen is that you'll add more rows, and then you'll need to you'll pick a column that you chose before because you overestimated the value of gamma j here. So you may go and choose this one and update this again. Another thing you can do instead is that you can actually, so here the step I solve for the one value that the one value that I thought was most likely for this column. But what I've done already is I've already selected a subset of these columns which I think are explanatory. I could find the set of these gammas in just these elements with given this set of rows best explain why. Solve them all at once, and this is still a least squares problem. If I have a 2 here, this is, even with this regularization term, it's still ridge regression, and I can still solve it with something that will look kind of like this. So I'll need a different notation to kind of capture the full matrix that of all the columns I've stored so far. But you can solve for all of these gamma values that you think are explanatory all at once. And then if one gets too small, maybe you snap it back to 0 or something like that. And this will be more robust than solving for each one at a time. So I can, and then it's just a for loop. So it's pretty easy to program these on these sorts of things. I have a couple of things I can try and do now. We have 10 minutes left. So one is,
One question about the x. So we have one x. First we transfer the s into our measure y, right?
yeah.
And then we use y and x to change them back if we need. Does these two x the same or we just randomly create one?
It's the same x. It needs to be the same x. So think of it as x is your hardware that's capturing the signals. So you know how your camera works. You know which sensor in the camera corresponds to what part of the image. So it's a fixed thing. Now you need to generate it randomly because if you did it in a way that was, if you pre-assigned, so if I chose x first, then I said, well, I can design an S such that y is all zeros. Right? So it won't work for every S. It'll only work with some high probability based on the randomness in there. So that's why the randomness comes in here. Otherwise, but in practice, you could probably choose it randomly once, build it into a hardware in your camera, and then run this and use it every time. So that X is fixed in this process.
Oh, it's fixed.
Yeah.
So, and we could use the same x for different kind of, like date we want.
Yeah, so you could then try and do a different, you have a different signal you're trying to measure, you can use the same X again.
Oh.
Yeah. So this is kind of like building, this is your hardware in your camera, this is what you get out, and you try and recover S. So I can try and write the code on the fly to try and do this technique where you solve for all the gammas at once, and we'll see if that works. I wrote some code for the frequent directions algorithm. I can show you how that works, or we could, end class a little bit early. So, any preferences? Okay, so I'll start with the simplest thing. I wrote this frequent directions code, and I'll show you. Okay, so here is, so here's the whole code for the frequent directions, and I'll kind of walk through this, and I'll show an example. But so you have input as a matrix A that's n by b, and L is the number of rows you're going to use. So again, you set this matrix B to be all zeros, an L by D matrix. And then I'm going to load in the first L minus 1 rows of A. Okay? So what I've done here is I've grabbed the first L1 minus 1 rows of B, and I've assigned them by the first L minus 1 rows of A. So instead of the I can use the semicolon to denote kind of an interval of all the rows that I want. And so again, this notation, it takes a little bit to get the hand on, but then it's very easy to copy a whole section of a matrix over in this way. Okay, and then I'm going to process everything else in A in this for loop, where I load in the last row of B with the next row in A, the ith one, as I go through the for loop. I take the SVD, as simple as calling this SVD command, and then I'm going to look at the last singular value of of the diagonal matrix from the SVD. And if it's greater than 0, if it's 0, then I don't need to do anything. I already have a matrix. I can just multiply by S and B, and I haven't changed the rank. But otherwise, I'm going to square it, and this is delta. And for all the other singular values, I'm going to subtract this delta from them. And I set the last one to be 0, just so I don't get a rounding error. And then I write B as S times transpose of B. Okay, so this was the code. I asked you if you could do this in an hour on Monday. I went and did this. It took me like 15 minutes. And I hadn't written MATLAB code for like a year, so hopefully, even if you haven't written it, it's pretty easy to do this. I think there are probably some small issues. You could probably make this more efficient in some ways, but it should work. So let's see if I have any. So let's try this matrix X. Okay. So let's say so A is equal So I've got 1,000 by 20 matrix A in here, and I can actually create its this SVD of A. Right, I don't want to print it all. I could print it all out, but it's going to be, U is going to be 1,000 by 1,000, so you don't want to see that. So if we just look at S, you'll see here are the singular values of S, and even they don't quite fit all on the screen. It tries to write out the full matrix here, which is kind of useless. Okay. Okay, so well, what I want to do is I want to, so now I want to run, so let's see if I do, so I can do S. There's probably some way to write these all to a vector. Yeah, so I can just write out the singular vectors like this. So I generated A as being completely random, and so I found one direction which is, and this is because it's not centered, which has a lot of the mass, and then all the other ones are going to be about the same. So this is not very interesting to recover. This is a very high rank matrix. So let's say, how do I generate a low rank one? So let's set S 99 to 50 S. That's right. S. So what I'm doing is I'm reassigning the singular values here to make them smaller.